So in this forward converter topology, we saw that the core reset is done in this way. When the transistor switch is off, the magnetizing current will flow in this path and dissipate in this resistor. Instead of dissipating in this resistor, which is lossy, we would like to put back that energy into the source so that it can be used later, so thereby increasing the efficiency. So for that, we would not like to have the resistance here. We will definitely have the diode. We need the diode, but we will change the topology a little bit. So let me rearrange the topology slightly, and we will try to do the core resetting in a magnetic way. So let me put one more additional winding like this here. I am showing this additional winding. They are all coupled. All these are coupled. In this fashion. One important change is the dot polarity. The dot polarity is in this direction, and I am going to indicate the turns ratio relationship as 1. What it basically means is, you saw that primary to secondary, it is 1:n. Primary to this winding is 1:1. Now this winding is called the demagnetizing winding. As the name suggests, it does just that job, demagnetizing the core or resetting the core. Therefore, in the literature, you will see that this winding is called the demagnetizing winding, and it is having the same turns ratio as the primary, and in fact it is wound bifilar together. That is, both the primary and the demagnetizing windings turns are taken together and wound together, so that the leakage inductance between these two is minimized. Okay, so now we have the diode, and let us place the diode here and make the connections. So after having made the connection, you see that this is the demagnetizing portion of the winding. The rest of the circuit is exactly same as the regular forward converter. We have changed only the portion corresponding to core reset part. The diode is there, the resistance has been replaced by another winding, and then it is connected to the supply. Very important, note the dot polarity. It is an opposite dot polarity with respect to the primary's dot polarity, which means that when this is positive, the end here is positive, and when this is negative, the end here is negative. Okay, now let us see how this functions. This particular type of topology is now called the lossless flux reset forward converter. So we can say it's a forward converter with lossless flux reset. Now this particular converter, the forward direction operation is exactly same as what we had discussed before. When the switch is on, you will see dot is at Vin with respect to the non-dot end. Secondary side becomes NVin, Vp will be NVin, inductance will charge, and during the period when the BJT is off, the non-dot end becomes positive, the secondary portion is out of the picture, inductance is freewheeling, and because the non-dot end is positive, here also in the demagnetizing winding, the non-dot end will be positive, and it will pump the magnetic energy in this path. So you will see that the magnetic energy will be put into the source. So the source has to have sinking capability, and it will go in this direction. So the voltage of this will rise correspondingly to turn on this diode and allow for the freewheeling path. So in this way the core will reset and will be brought back to the original status, and then the next cycle will start again. During the time when the core is resetting, that is when there is a current flow, demagnetizing current flow during this, you see that the diode is on and this end is connected to ground. This end is connected to V in. So the voltage across this winding is V in. So which means a constant voltage is applied across V in, and the core reset happens with a constant rate, and that is V in by L. Of this particular winding, or V in by Nd. If there is Nd is the number of turns in this demagnetizing winding, we can say V in by Nd will be the rate at which the flux decreases to 0. So you see that when the transistor is on, V in by Np is the rate at which the flux increases, and when the transistor goes off, V in by Nd is the rate at which it comes down. And as we are saying that Nd and Np are same number of turns, 1:1, then the rate at which it increases and the rate at which it falls is same, and therefore the maximum duty cycle that you can offer for this type of converter is 50% duty cycle, because at 50% the flux would have reached a particular level, and you should allow remaining 50% of time for it to come back to 0. Less than 50%, no problem, because the off time is greater than the on time, and it will definitely come back to 0. So this is one limitation of this converter. It has a maximum duty cycle of 50%. Now the waveform, all the waveforms are exactly similar as the previous, except the demagnetizing waveform. It was exponential in the earlier case, exponentially decaying to 0. In this case, it will linearly decrease to 0 because the voltage across this winding is constant. Let us have a look at this waveform by simulating the circuit, and probably you can also do the simulation and find out the waveforms of other parts of the circuit and ensure that they work similar to the lossy flux reset type of forward converter also. I shall briefly show to you the lossless reset forward converter that we just discussed, and see how we can do the simulation of that one. So I have created another folder called forward 2, which I have copied from the lossy forward converter circuit, and I have modified the schematic to include the demagnetizing winding that we just discussed. So let me expand this point. So you see all the part of the forward converter is exactly same. Here too it is same, the gate drive portion. There was a diode resistor for core reset. Now that portion we have removed, and we have included one more winding. So this is the new component which I have picked from the library here. So what I have actually picked is a transformer for forward converter, which is having 3 windings, and the dot polarities. Observe the dot polarities. The primary and the secondary have the same sense of dot polarity, and the demagnetizing winding is the opposite sense of dot polarity, and exactly that is what we are using. And to the demagnetizer winding I have connected a diode, and as before I have connected the 0 voltage sources to act as current sensors. VIQ and VIS we saw in the last simulation, and I have put VID along with this diode, and as the current direction is going in this direction, as the arrow is moving, I have put the plus sign here such that the current enters the plus sign. Now we can look at the currents here and see that the demagnetizing winding is just like what we have discussed. The rest of the circuit will remain the same. So we go back to the terminal and let me do the netlist. And now that the netlist is created, ngspice forward.cir. So that is loaded into the spice. Run the simulation. Observe that I have given the initial condition here just like from last time, so that the simulation is very quick and we will be able to see the results quickly. So set, I will give the background color equals white. Set the color of the foreground to black, and plot the current of PID, demagnetizing winding, current of the switch, and the current through the secondary. So you are now able to see the blue one is the current of the switch, and this flat equivalent flat top value will be 2 times I naught. This will be I naught. This is Ni naught, 2 in this case. And you see here the demagnetizing winding. Let me explore that a bit, zoom in, and you will see that it is linear. So you see that it would be having a linear slope. The forward slope is also linear, the falling slope is also linear, because the voltage across the winding is fixed, constant, and it would have decayed by then. Because this is a less than 50% duty cycle, this would have taken around the same time to come down to 0. Now let me also show you one more change in the waveform that will occur is the wave shape across VIQ, across the switch. There will not be the exponential portion which you observed in the lossy flux reset forward converter. When this switch is off, this diode is conducting, there is a V in coming across here, which will get reflected onto this. This is positive V in, this will be positive V in. So there is a V in here and a V in there. So there will be 2 times V in coming across this. So let us see that waveform 2. Plot VQ. So you see that this is the V in value. Now up to this point, we see that there is a steady decay in the linear decay in the magnetizing flux, and that value is 2 times V in. This value is V in, which is 15 volts is V in, and this is around 30, plus the diode drops, and then at this point diode stops conducting, and this exponentially drops to 0, and this is the voltage potential that it will finally settle at. It should in effect ideally drop to 0 directly, but because their switches are not ideal switches, you will see that it will drop to 0 in a finite time. So this way you can simulate and learn more about the circuit by playing around with that one. So as you can see, this is the lossless core reset type of forward converter. There is one problem in this, and that is the issue of leakage inductance. So there will be some leakage inductance here. Leakage inductance means that that portion of the flux that is not coupled across between the 2 coils, and we mentioned and we discussed that this will be 1:1:n, and both the primary and the demagnetizing winding will be tightly coupled. Now, during the time when the switch is on, when Q is on, there will be a current flow through the switch like this, and I will call this as I primary, IP. And IP contains the reflected component from the secondary and also the magnetizing part. Now, the moment the switch goes off, the reflected part anyway cuts off, the magnetizing part cuts off to 0. Now, across this leakage inductance, which is not coupled to the demagnetizing winding, we'll see a sudden cut in the current, and therefore a huge di by dt. But the coupled part of the magnetizing current will flow through this demagnetizing winding into the supply and then back, so it will freewheel through this and then decay. That we have seen. But the uncoupled part, there will be some leakage inductance, and that will give rise to an LDI by dt drop. LDI by dt drop. Now, this drop would have a reversal of polarity. This would be plus and this would be minus, because the current has gone from positive to 0. So it's a negative slope, huge negative slope, because in a short time it cuts out to 0. And that drop will plus V in will come across the Q. So you would see when the transistor is on, when the transistor goes off, it should normally go like this. But during the time when it switches off, because of this leakage inductance, you can expect a very huge spike repetitively occurring, and would appear like this, depending upon the level of the leakage inductance energy that is stored in that leakage inductance. So this can blow the transistor Q, and that is undesirable, and that should be taken care of, that should be addressed. So to take care of that, what we do is that and still continue to be lossless, we use one more transistor. I will show how we construct that topology shortly and address the issue of this leakage inductance. Consider the topology like this. Both Q1 and Q2 are in series with the primary like this. This is a forward converter. The dot polarities, note the dot polarities, and also see that the secondary side is the typical buck converter circuit. Now, whenever you operate, both Q1 and Q2 are turned on together. So the moment Q1 and Q2 are turned on together, there is a current flow through the primary like this. Primary is seeing the dot end of the primary is connected to V in, the non-dot end is connected to ground. V in appears across primary, N V in appears across the secondary. Normal forward converter operation happens. Now let us say we have leakage inductance, and we also have to incorporate core resetting. So we will include two more devices in this. So let us say Q1 and Q2 have been turned on. There is a current flow in this direction, as shown by the green arrow. Now at this moment, Q2 and Q1 and Q2 both are turned off together. Now current flows along as shown here. Then at this point, Q2 is off. We will take a branch out here, and push it to the supply through this diode, and another diode here, like this. Recall that there is a battery which is capable of sinking current connected here, and that is important for the operation of these type of circuits. So if you look at this circuit now, so Q1 and Q2 are on, there was a current flowing in this direction as shown by this pointer, and now Q1 and Q2 are suddenly switched off. The current continues to flow in the same direction in the inductor and the leakage inductance, then follows this diode path into the supply, charges up the supply into the ground, back up through this diode, and enters the inductor the same direction. So you will see that the inductor current continues to flow in the same direction, and even if there is leakage present, it will not hurt or it will not result in a spike, because you are not breaking the current conduction path, and therefore there is no high LDI by dt voltage developed across the leakage inductance. And this way the voltage drops across both the transistors will be contained, and when the switches are off, this point is connected to ground and the other point is connected to Vin. This will see Vin, and this point is connected to Vin, and therefore Q2 will also see a drop of Vin. So both should have a voltage withstanding capability of Vin. So this is a dual transistor forward converter, very interesting circuit. It is lossless, and it can also handle leakage inductance issues. So this is a converter that you can practically try out.